Okay, yeah, it's starting to counting down, so it's my session begin. Thanks so much for coming. Yeah, and yeah, I'm the first speaker of in this room, and I'm the first one to introduce what is RL to everyone. So I do a favor to the following speakers. You guys do not need to introduce what is RL again, okay? So today my topic is optimizing large-scale RL with SGLang. Look at this title. What is large-scale RL? When we are saying about training, we say large-scale is like gigantic model, vast data, complex usability. Yeah, any kind of thing you can imagine regarding large-scale will happen in the large-scale RL. Okay, so that's the topic today. We got to cover how we are using SGLang in industrial level large-scale RL, and we want to introduce SGLang's features that optimize the end-to-end RL pipeline. And thanks so much for listening to the introduction. Yeah, and the quick introduction of myself is that I'm Chenyang. Right now, I'm a PhD student at UCLA, and I'm working on RL maybe for specifically RL systems for over 1 year. And we're gonna cover 4 critical system optimization today. Yeah, so before I dive into the optimization, I want to do a quick survey. Okay, look at these words. The first thing, have any of you guys tried to launch your RL jobs, or just an example for maybe a lot of you guys know the concept of Search R1. Have any of you guys launched the example of Search R1 with your RL frameworks? And the second thing, have you heard about the words like the reward function? And have you ever tried to modify or customize your own sampling logics? And the final thing, the fantastic words, or fancy words like important sampling. Have you guys heard about these kinds of concepts? And the third thing, have any of you guys tried to customize your model? Like, say you have a llama model and you have a queen model, then maybe you change some of the architecture of that model. Have you tried to set up your RL's architecture and train your customized model? So, if you have done any kind of thing in the 3 points, you must have hit the wall of the performance. So if you have done that, have you profiled why your RL seems to be slow or not efficient, and and maybe your reward collapse? Have you tried to debug with your RL systems and try to say what is the bottleneck? So for these 4 points, if you have done all of it, you're an expert, and I inspire it, so you should come and join us for the open source community. But if you haven't done any of this, hope we can expand our idea to you and getting some insights today. Okay, so this is the 5 parts I gotta cover. Okay, the first thing is the incorporating SGLang with RL. So let me guide you through the SGLang's feature of RL systems, and before that, we can see a quick introduction of what is an RL systems. Here I list several of these kinds of state-of-the-art RL systems. The first one is Vero, maybe from the version maybe 3 months ago, and this one is I think it's a real, right? It looks quite structuralized, okay. And this one, okay, this one splits RL frameworks into blocks, and they have the storage and they have the data flow. And the final one maybe is the most simple but straightforward one. It's just a loop across a bunch of concepts. So what is a typical RL lifecycle? At least 5 concepts in the RL traditionally. The first one is rolling outs. This is I think it's a terminology used for RL, but you can just imagine this is inference. You have an inference engine, and you use the model weights to generate answers to the prompts. But in the scenario of large scale, the rolling out isn't just a prompt and answer, since the answer should be quite complicated. For example, this slice is generated by the Gamma, right? Gamma is somehow like an agentic PowerPoint company or whatever. So if I want to generate a PowerPoint with Gamma, it shall first see what my concept is and generate some tool code maybe for its picture generator, and generate some tool code maybe for its the aligner to make sure its lines are aligned properly, right? So take this example. A single prompt maybe results in tens or even hundreds of tool calls into one single request, and each tool call will tell the corresponding tool and wait for it to return, and they're interacting with you again and again. So this rolling out is quite like you are diving into a deep research agent. It's not just a chatbot. Yeah. The second thing is evaluation. It covers like the reward, value, KO, diverge, and advantage. You do not need to know what in detail they are, but they are critical for you to calculate the loss for your training. And the third thing is the storage. Okay, typically people do not have a storage layer in the RL frameworks, but I listed here since, and I said, the rolling out is quite complicated. You may not always have the time for your rolling outs to finish. So in a lot of scenarios, we may stop the rolling outs in specific points, and in maybe later we got to continue the generation. So we have a storage layer that to cache these kinds of unfinished or even finished one for you to analyze, reuse, and to debugging. Okay, that's the storage layer. And the training, of course, the Megatron or FSTP or Torch Titan. Yeah, today is PyTorch conference, so okay, you guys may be familiar with these kinds of concepts. Yeah, it's just the training. And the final thing is refit. Refit is a terminology that I tend to use, but people may have something like the weight updates. I personally think that refit is the most accurate words to describe. Because if you're saying it's a weight update, it looks like you are training the model, but the model have already been trained. So the word refit means after the model have already been trained in your training backend, you want to copy the model weights back to the inference. Since we are doing online and on-policy training, if you are using the wrong if you do not update the weights in your inference engine, you are not sampling with the latest model. Yeah, that's not in our assumption of our current RL style. So the words refit, copying the weights from training engine back to the inference engine and do another rounds of rolling outs. And in the cycle, have these 5 parts together. We have the RL lifecycle. So remember this RL lifecycle. We can take back to this picture, right? It is exactly what I'm describing. So this is the rolling out part. It's using SGLang to get samples and get sequence. And this is like the evaluation part, and this is data storage. And after that, we have the training part, and then we copy the weights back to the inference engine. So that's the RL lifecycle. Exactly speaking, that every picture here is doing in this 5 lifecycle, but they are picturing their architecture in different ways. Yeah. So given the concept of RL, why we are advocating SGLang for your RL lifecycle management? From my point of view, I think the best to have is that SGLang is a library for you to do your RL job. It's not a framework. Say, I heard the words from DeepMind that we tend to make a library but not a framework. For framework, it's trying to teach your users how to do some rigid things. And if you do not follow the framework's requirements, you might get something wrong. But for library, it's customizable and easy to use and open to use and give you the freedom to implement any kinds of your imaginary utilities. Okay, so and 5, we have detailed concepts. The first thing is open to use refit functionality. Just as I said, to copy the weights back to the inference engine, we have 3 methodologies. And the second thing is easy to postpone generation. Again, when we have some, for large-scale rolling outs, at some point we may want to stop our generation. So SGLang gives you the API, then you get easy to stop it at once. And the third thing is the fine-grained engine sleep and wake up. I got to cover it later. It just means that we have the SOTA context switching technologies to facilitate your RL. Okay, and the fourth thing is the training server alignment. For example, if your company is using SGLang to serving your online jobs, it's better to have SGLang both for the training and both for the serving. That makes your serving and your training aligned. The model you see during the training is the model you use for your serving. And the final thing is the load balancing router. That means for these kinds of complicated rolling outs, we have unified and single endpoint for the generation. You do not need to care about in detail which where does the request go to each of the worker? That makes your job quite complicated. You just need to send to the router, and router controls all the SGLang generation. So yeah, let me first, this is the introduction parts, and I have 2 parts for the, yeah, it's much easier to understand. The first part I want to introduce is the partial rolling out. Take the step back. Just as I said, if we have an agent, and the agent shall generate maybe tens or even thousands of tool code to the environment, it's quite slow, right? Maybe some tool they just broke down, and you cannot get the response in 1 minute. So how can you make sure that your generation is efficient? So that's the idea of partial rolling outs. We can imagine that imagine that in this kind of scenario, some of the requests is quite slow, and maybe a bunch of requests, they are normal and they return quite quick. So we have a picture called we have a picture to demonstrate what's the diversity of the responses. We can look at this picture on the left. This picture is the CDF of the response return time. That means maybe we send 100 requests to the environment, to the generation, to the rolling out time, and how quick the response will be finished. And we found something interesting in that 80% of the response will return just in the first 50% of time. That means for the last 50% of time, we just used it for the 20% of request. So take these things in mind. It's just like the 20 and 80 law common use, right? Most of the requests they finish quick, but some of the requests they are slow. And since RL, traditionally we need to wait for all the requests to finish and then go into the next step. How can we optimize this? A basic idea is oversampling. It just means like if the first 80% of requests come back so quick, why cannot we send in more requests than we expected? And we get the first return ones to us, and then we use these ones for training. So that's the chief idea of partial rolling outs and a lot of words you have been hearing. We do an oversampling, and when the request returns to us to a specific point, we postpone the unfinished one. Okay, the most direct idea is that we can through this unfinished one and training with these kinds of returned ones. Yeah, we still have adequate requests to train our model. And a more dedicated usage is like we use these kinds of unfinished ones, cache them onto the storage. And in the next time, we first get these unfinished ones from our cache, and we let these prompts in the cache to finish first. So that's the idea of oversampling and partial rolling outs. Yeah, this picture explains it in the clear way. In upper bound, we see that all the engines, they are waiting for the response 6 to finish. But if we're using partial rolling outs, we can just, at some point, if the request is adequate, we just stop all the generation and load this kind of unfinished one in the next parts. Yeah, that's the first part of partial rolling outs. And another hitting point I've been hearing these days is training inference mismatch. It's quite like a favorable fashion words. So let me first describe what is training inference mismatch. Training inference mismatch means that the log probability for a given string inside the inference or the rolling outs should be different from that inside the training. In other words, if you give the same prompts to SGLang and give the same prompt to Megatron, you get the same log probability. Ideally speaking, they should be the same, but technically speaking, they are not the same. So that's the training inference mismatch. And training inference mismatch is causing a lot of jobs to fail these days, and we are using important sampling to fix it. And after I describe what is training inference mismatch, we can imagine what's the reason behind this. Well, yeah, ideally speaking, everything should be exactly the same, right? You have the same model parameter. You have the same prompt to the model. Why they are not the same? We have several concepts to share. The first thing is the non-associative float point arithmetic adding. We all know that A plus B is not always equal to B plus A for floating points, right? And we know that for LLM, O-reduce is commonly used. O-reduce is commonly used. If you have 4 GPUs for the model, you first reduce the GPU 1 and GPU 2, reduce GPU 3 and GPU 4, and you reduce them together. And the results may be different than you reduce the first one and the third one, and the second one, the fourth one. So these kinds of reduced order would introduce like the thing like the non-associative, the flow point adding. And layer by layer, maybe you are using different ways of, you have different ways of O-reduce. So the difference just gets accumulated. And finally, we found that the log probability has slightly different. In the beginning, people think that this kind of slight difference may not be a same, but to some points, we found out that for extreme tokens, the log probability could go to something we cannot sustain. Okay. Yeah, so another point I want to point out is, just as I said, for MoE models, these kinds of training inference mismatch is rather worse, since MoE models, they have their gating, or the router, right? The router should design which expert in this layer it will go to. So the slightly different maybe in the expert selection, because layer by layer also introduce another kinds of the training inference mismatch. So also, that's the results of training inference mismatch and the behavior. Yeah, after I describe this, we found that it's a pure system problem, because our kernels are not aligned maybe in the training and inference. So we have these kinds of misalignment. How can we fix it? The first way that solve it directly in the system side. So we have a bunch of words coming from the community. The first idea is that for the Thinking Machine Lab, they introduced the concept of the deterministic kernel. So the deterministic kernel is just as I said. They want the results to be fixed for the O-reduce order. So in whatever ways you want to do the O-reduce, the result will be still the same. So that's amazing job. And their results turn to be, they can make the same deterministic, but it's far away from the training inference mismatch. So how does it? It's like the non-deterministic just means if you give the same input to the same engine, maybe you give the same input to SGLang, and you get the results twice. You found that these two results are not the same. The same as FSDP. Give the same prompt to FSDP and forward it for twice, but these two log probability may not be the same. So deterministic kernel just means that given the same model, given the same engine, given the same hardware system, and given the same prompt to get the same results. If you do not using the same engine, it does not give you the same results. And even if you use the same engine, say you use Magtron on A100, or you use Magtron on H100, the results will still not be the same. So it's far away from solving the problem of training inference mismatch. Yeah. Another way is like, if the difference is between Magtron and SGLang, why cannot we using SGLang for training? Or why cannot we using Magtron for the inference? I just take Magtron for inference, for example. It's not possible since inference and the training, they are quite different. For training, no one ever using KV cache, right? Your model is frequently be updated. Your KV cache will be easy to be invalid. So the training and inference is quite different for LLMs. But maybe for diffusion model, they are not the same. But since we only discussed the training, the area of the LLMs, so it is really hard for you to using Magtron or using SGLang to do other guys' work. Okay, so that's not even possible for that's the two solution on the system side, and we found it's not the perfect one. And we still go further. We want to do it. We want to fix these problems on the algorithm side. So that's introduced the concepts of the importance sampling. It's a commonly used methodology in the RL scenario that we just using the probability of the sampler as the under the probability of the actual learner. So that's the solution of the importance sampling. Yeah, we can see that. We can imagine that if we want to writing kernels to fix the problems, we shall introduce maybe tens of thousands of lines. But this kind of importance sampling looks quite elegant, right? And in detail, we need write no more than 100 lines to just fix the problem. So personally, I love this kind of algorithm solution. And there are some good points for this solution in that we found it for low precision training. For FP8, if you're using Mactron forwarding FP8 and backwarding FP8, the important sampling will be even better. It can make your dead job alive again. Okay, quite interesting, right? We are still working on this, and hopefully we got to have some results, technical reports with our collaborator in ByteDance and both in the open source community. Yeah, and that's the training inference mismatch. So this is the second part. Okay. And I still have 4 minutes to go, so let me introduce another kind of easy to understand concepts. A CUDA graph aware model weight wake up. So what is weight wake up? Let's first see this, right? For the RL, we have inference and we have a training. Could we always put the inference and the training on the same GPU? Like we have an unlimited GPU, right? We put SGLang on that GPU and we put FSDP on that GPU and we let it always run forever. Is it possible? Actually not. First, we do not have this kind of unlimited GPU. And another is that for inference side, we want to expand the KV cache as large as possible to speed up the inference. So if you just give a small amount of GPU for the KV cache, the inference would actually be too slow. Okay, so that makes we cannot feed them on the same GPU. So the first idea is that we have to switch them, right? In the inference, we launch SGLang, and in the training, we launch FSDP or Mactron. But is it really that simple? So we can imagine that just kill SGLang and relaunch SGLang takes really a long time. So does for Mactron. So the concept is like a kill and relaunch, but we want to make further optimization for this. And we dive into it to find what is actually causing the time for the offloading and uploading. And we found the central concepts is a CUDA graph of SGLang. We offloading SGLang's model weights and we offloading SGLang's KV cache. They are quite quick, but for the CUDA graph, if you once break it and you rebuild it, it takes a really long time. So what is a CUDA graph? In one line of explanation, CUDA graph is GPU trying to remember the data flow's direction. It should remember the address of the data flying from this point to that point. So the address or the virtual memory address is the center to make sure your CUDA graph alive. And that's the point. We want to, when we are doing the context switching, we want to make it quick and we want to always keep our CUDA graph alive. So we need to keep the virtual memory always unchanged. Let's introduce our job. We call it torch memory saver. Torch memory saver, it creates a region for you to protect the tensor. And once you release the tensor's physical allocation, it will record the virtual memory address of that tensor. And again, when you recreate this tensor back, the physical address will be changed, but the virtual memory address will be consistent. So as long as your virtual memory address is consistent, your CUDA graph, the address is remembered, is still the same, right? So that's the perfect thing we have. So that's the point, is the CUDA graph aware model waking up. We use torch memory saver to protect the virtual memory address of serving model and the KV cache. So we have this PowerPoint. On the first stage is the rolling outs. Right, and after rolling out, we offload SGLang's serving model and SGLang's KV cache, and we are doing the training. Remember, the CUDA graph of SGLang is still here, right? And after the training, we wanted to do the refit. So we have to upload SGLang's serving model and SGLang's KV cache back, and we gradually copy in the training model's parameter back to the serving model's parameter. Yeah, so that's the refit part. And after the refit, we offload the training model parameter, and when we do the generation, we do the rolling outs again. It looks perfect, right? We have the CUDA graph, and we have a dynamic offloading and uploading. But what's left? We can see the red parts here, right? The red part cannot be used. Why? It's quite interesting, because if we want the KV cache to expand to occupy the red parts, its virtual memory address will be changed. The size of the KV cache will be changed, so the virtual memory cannot be protected. So our torch memory saver will be invalid. So that's the tragedy we do not want to make. So if we wake up the serving model parameter and the KV cache at the same time, we cannot use the left part for the KV cache. So that's introduced another stage of the optimization. we wake up the KV cache and the serving model parameter separately. Okay, see the difference. On the central line, we first wake up the serving model and do the refit. And after the refit, we offload the training model parameter, and then we upload the KV cache. Through the whole process, the KV cache will never be expanded, so its size will not be changed. So the virtual memory address will be still saved. So that's a good point. We can using the full memory both for training and both for the inference. And we always keep the CUDA graph alive, and the rolling out is quite quick. So that's the optimization we made through the journey. Yeah, thanks. And I made the points. Okay. Yeah. For the left parts, it won't be dived today, but yeah, I'm happy if you have any question regarding the points I've said. And it's quite a general optimization. It can utilize for any RL frameworks or any RL jobs. So hope this can facilitate your job. Thanks.
Have a lot of jobs per training batch, then the straggler should take a less percentage. So I'm just curious about like how many jobs you're putting there in the whole RL framework at the same time, like as an epoch.
Your question, like how many jobs we put in the RL job in the RL?
Yeah, in an epoch.
It's quite a confident. Okay, so the actual thing that for specific company, they are training their model and the agent for thousands of steps and across thousands of GPUs for over 3,000 steps. So the training is really at a large scale. It takes maybe a whole week to do the training.
So 3,000 steps means like 3,000 turns, right? So for one agent program, it runs 3,000 turns, or like.
Sorry, the step is the training. The step is the training. Is for the training, but for the turns, I don't remember the exact turn requirement. But you can imagine that there will be hundreds of turns for a single interaction. Yeah.
Oh yeah. But I was saying like if you only have 2 requests in an epoch, then like the longer request is always the straggler, right? So I'm just curious about like how many requests you're putting there. But like, do you have an estimate for the scale or?
Maybe it's hard for me to review this.
We can talk offline. Thanks.
Yeah. Thanks. Oh, please. Sorry, pardon?
If you are just dropping the long tail like rollouts, the easy possible that is going to affect your. It's actually the long tail rollout is actually finding the rewards.
Great points. Yeah, there's no free lunch for this kind of long tail effect. In some specific use case, we do not need this kind of long tail one since we will always give no reward for this long tail. So it makes sense. But if this kind of long tail sequence, you gotta give long rewards. We still have ways to optimize this, like the PowerPoint this here. This is the pack. I think it's the road packer from the Alibaba team. So their idea is that they cache all the long-tailed prompts into the cache. Remember that they do not record the already generated one. They just discard it. So they have a batch. So gradually they will have a batch of long prompts. And for some specific step, they get all the long rollouts out and then do all the long rollouts at that steps. So that's their methodology to mitigate the thing as you speak. Yeah. Thanks.